Hello everyone, this is Heading Tian. This video, let's learn Chapter 4.1, Exponential Function. F of x equals b to the x. So if you see the form like this, we call this is exponential function. So the exponent part is a variable. So x is a variable, b is constant, is given information. b is greater than 0 and b is not equal to 1. We have a special line we call horizontal asymptotes for all the exponential function. What is the horizontal asymptotes? In the chapter 3 rational function part, we have learned horizontal asymptotes, vertical asymptotes. Horizontal asymptotes is a horizontal line, y equals b. My graph getting close to it, but never touch it. So that means as my x approaches positive infinity or negative infinity, my y's value approaches a special number, for example, b. So y equals b is my horizontal asymptotes. So this is a review. Okay, so let's see how to graph a exponential function. If I have a function f of x equals 2 to the x power, we can plot some points. So we can, so here is a table. First row, they are all the x value. And let's see what are the y's value for these x value. We can evaluate y's value when the x equals negative 2. 2 to the negative 2 equals, power is negative, then I move the 2 to the bottom and raise it to the positive 2 power. We have 1/4. And second, f of negative 1 equals 2 to the negative 1. We need to flip the 2 to the bottom, raise to the first power, which is 1/2. If I have f of 0, 2 to the 0, it is 1. So that means it doesn't matter what is the base. If I have a 0 power, it is 1. And the next, we can evaluate f of 1. So let's put 1 here. 2 to the first power, 2. And f of 2, 2 squared, 4. So we got 5 key points. Let's plot the key point on my graph. First one is negative 2 1/4. It's the point here. Negative 1 1/2, 0 1, 1 2, 2 4. Let's use a smooth curve, connect them. It's not that smooth. Okay, then what is the horizontal asymptotes if I see the graph? The definition is there is a horizontal line. My graph is getting close to it. Obviously, from the graph, you can tell the horizontal asymptotes y equals 0. So how to prove? The definition is my horizontal asymptotes when the x approaches infinity or negative infinity, and my f of x approaches a special value. So y equals b is the horizontal asymptotes. So from my graph, I can prove that y equals 0 is horizontal asymptotes. I can input negative infinity in my function. So 2 to the negative infinity, negative power, bring the 2 to the bottom. So I'm having 1 divided by 2 to the infinity. So 2 to the infinity, that is infinity. So 1 divided by a huge number, that means approaches 0. Because I know 1 divided by 1,0,0,0,1, I'm having 0.000001. So as my bottom approaches infinity, my number here approaches 0. Okay, so horizontal asymptotes, y equals 1. If I move my graph horizontally, move to the left, right, move to the right, left. So my horizontal asymptotes keep the same. Spam phone call. So let's decide domain and the range of the function. Domain means all the x value. So looking at all the x value, I'm looking at the point on the most left. My graph all the way going to the left. So the smallest x value approaches negative infinity. So my domain is all the x values starting from negative infinity. And then on the right hand side, so to the most right, the number x approaches positive infinity. Domain is all real numbers. How about range? Range means all the y's value. Lowest point. Where is the lowest point? There is a point getting close to the horizontal asymptotes. So the smallest y's value approaches 0. It's not equal to 0. And then all the way going up on the right hand side. So the range is from 0 to infinity. And the horizontal asymptotes, we talked about this, y equals 0. How about if I have the different b? We talked about the b equals 2. How about b is greater than 1? Or the b is between 0 and 1. B will never be a negative number. All right, so if the b is greater than 1, for example, my function f of x equals 2 to the x, f of x equals 100 to the x. So we are all having an increasing function. If the b is between 0 and 1, for example, I have f of x equals 1/2 to the x. F of x equals 0.7 to the x. So the base is b, is between 0 and 1. We are having a decreasing function. For all the exponential function, increasing or decreasing, the b is between 0 and 1 or greater than 1. We all have a special point. They all go through a special point, which is 0, 1. Because if I have function f of x equals b to the x, input x value equal to 0, b to the 0 power, it is 1. So the point is 0, 1. The exponential constant e, if I have a function f of x equals e, e to the x, the e is about 2.718 and etc. numbers. Then we are having increasing function because the e is greater than 1. The base e is greater than 1. So we are having an increasing function. And also my graph will go through the point 0, 1. Okay, let's see. Example, f of x equals 3 to the x. Find the graph. So it's not shown from the graph which one is f of x, g of x, or h of x. But I know that if I'm graphing the f of x equals 3 to the x, 3 is greater than 1. I'm having an increasing function, and we'll go through the point 0, 1. So this graph, so the right one, go through the 0, 1. This one could be, it is my f of x. I can also test some other points. Input, for example, input 1. What is the y's value? 3 to the first power. It is 3. The point is 1, 3. So 1, 3. This is 1, 3. Yes. So the right curve is my f of x. And how about finding the g of x and the h of x? So since we find 2 key points for the f, I can list them in the t-chart. This is x, this is f of x, and first point is 0, 1, 1, 3. And then let's see the g of x. g of x, we have 3 to the x minus 2. What is the transformation? Is there any y changing or the x changing? So here, in the original function, the x is here. If I have the horizontal shifting, shrinking, or reflecting, I will change my x here. That means if I change something in the x, the new function, I say r of x. The y didn't change, so only do something here on the x part. So I can say 2x plus 3. So only changing is the x part. So this is the horizontal shifting, shrinking, or reflecting, for example, negative. So let's see the first one, g of x. What is the transformation? So that must be the x changing. So my x minus 2, that means I'm moving to my to the left or right 2 unit. Minus 2, moving to the right 2 unit. So g of x equals 3 to the x minus 2. That means I'm moving my graph based on the f of x to the right 2 unit. Also means all the x plus 2. So based on these two x value plus 2, I'm getting a new graph x g of x 2, 3, because add 2 on the x, 1, 3. So the key point there are 2, 1. So 2, 1, 3, 3, 3. Okay, the blue curve is the g of x. So without any computation, I will say h of x is the green curve, but we can also prove it. So this is 1, this is 2. I'm looking at the h of x equals 2 times what? 3 to the x plus 4. What is 3 to the x? Original function f of x. Okay, that means the y's value changed. I can also rewrite it. That's 2 times f of x plus 4. So only y changed. First, you see 2 times f of x. We are stretched vertically. Step 1, we already got the 1 and 2. We say step A. Stretch vertically, all the y's value multiply by 2. And then second transformation B. Plus 4 means vertically shifting. Move up for unit, all the y plus 4. Then I'm having a new table. So based on the mother function's key points, based on these two key points, x and h of x, let's find the new points. So x didn't change. All the y times 2 plus 4. 1 times 2 plus 4. 3 times 2 plus 4. What is the new key point? 0, 6 and 0, 10. So 0, 6, 0, oh, sorry, I changed the data. This is 1. Do not change the value of the x. 1, 10. So yes, the green curve is a function h of x. So you can describe that. We are stretching vertically 2 times and then move up for unit. All right.